you would like to learn a little bit about how is this a follow-up course entitled the laboratory course for simulation, or I think it is called simulation, a laboratory course, if I remember that correctly. That's uh, that's a course we're still gonna look at the subject matter of simulation, but more in a practical point of view. So it's not that much anymore about the theory of multi-body system dynamics, but it's more about what is that we can do with the knowledge we learn from this course. But I will get back to that in the end of my lecture today. So, lecture ID 12. Uh, lecture ID 12. So it's last one. It's the last one. It's kind of weird because it felt like it was 2 weeks back when I started to do this streaming, and now it's the last one. Somehow it's a little bit hard for me to believe that it been 13 lectures. Well, I guess that's the case, but okay. So what we will do today is that we're going to look a little bit about the subject matter that is a real-time simulation. Real-time simulation sounds like something extremely sophisticated, something that is difficult to understand what the heck is going on in a real-time simulation, but it's very simple. It's just the equations we have learned to develop, so equations of motion. And what we're going to do is that we're going to simply synchronize the solution to actual time, and that's what it makes it possible to read the signal from the user and do something that is very useful in software development and software testing. That's what we're going to learn today. And there is a comment about this upcoming course. Like mentioned, I will get back to that. And thank you very much for that comment that you will enroll just to see how is my streaming developments. Yeah, it will be interesting you to see because definitely I'm gonna get my camera in a business. This guy will be in a business. Maybe I will do some other tricks. So I recommend you to enroll just to see how is my YouTube career progressing. Okay, with that, let's move on to summary from the last week lecture. So last week we looked a little bit about how is modeling of flexible bodies, and we concluded that there are two alternative ways to do it. So we can use a method that is not strictly speaking in a theory of the flexible multibody dynamics, but it's based on rigid multibody systems. And the method is called landmass approach, and as the title implies, this one here, it is a method where you're using rigid bodies, lamp masses if you may, and these lamp masses, rigid bodies are connected together via spring elements. The spring elements will introduce the flexibility to all to 6 degrees of freedom in a spatial case, 3 degrees of freedom in a planar case. And it's something that you can use to model beam-like bodies, mainly beam-like bodies. There are some examples which shows that this method being applied to plates as well. But for plates, it's become to be very, very complicated because there's going to be a lot of springs traveling back and forth if there's a 4 bodies like this, or if 6 bodies like this. Excuse me. How this spring's supposed to be made in order to make this according to reality. There's going to be a lot of springs because the high number of the springs, this method is not really, I mean, if you want, you could apply that to plate-like structures, but really it's not making much of a sense. So is it on its best when you apply that to beam-like bodies like this one here? So this is a simple beam-like body. And now the beauty of the method is the fact that there is exactly the same we learned in the case of rigid multibody system dynamics. So it just keep on increasing the number of bodies, number of unknowns. That's the better way to express it. And that means that the system matrix will become bigger because the mass matrix will become bigger, and vector of external applied forces will be significantly larger as well. So that will be the way to model flexibility based on land mass approach. Not frequently used anymore. Every now and then it's used when you wanted to model, let's say, wire ropes or something that otherwise is very difficult to do. But but in a real practical modeling cases, the most often used method is the floating frame reference formulation. Concept of this formulation is to combine multibody system dynamics, multibody system dynamics and finite element model. And the deformation is described by using finite element method. And large reference motion, rigid body motion, if you wanted to call it that way, is described by using multibody system dynamics. Now, the thing you need to do to this finite element model is that you have to reduce the size of a typical finite element model. A reason being that finite element model easily consists of, say, 10,000 degrees of freedom, 100,000 degrees of freedom, even million degrees of freedom. And that's not matching well to multibody system dynamics, where the reference motion, which is usually the most dominated in terms of dynamics, is described by 6 coordinates and 7 coordinates if you're using 4 rotational parameters. So usually you need to do something to reduce the size of your finite element model. And like I mentioned last week, what you can do is that you can use a model reduction technique. In a model reduction technique, you're kind of looking at what are the deformation features of your structure. And these features, you can figure it out by using an eigenvalue analysis. You know that if you have a finite element model with 100,000 degrees of freedom, it means that there's 100,000 different deformation modes and corresponding frequencies. And some of them, many of them actually, are not important in terms of dynamic performance. So those ones that are less important, you can easily just ignore it. And that's what the model reduction is about. So you're kind of looking at all the features, and then you're picking up the ones that you feel that are the most important. How you can do it? Well, that's a little bit of challenge. There are some techniques that helps you to do this decision, but generally speaking, not that easy. So some of the modes are important, some of the modes not so important. So let's look at an example. So here is a beam-like structure. This is actually a hydraulic driven structure where this end is here connected to pilar body that is going downwards. And then there is a hydraulic cylinder that connects the pilar and this flexible body. And now if you look at how are the lowest deformation modes, I mean frequency-wise lowest, they actually are the ones that are contributing quite a bit about how the system behaves. Like just to give you an example, if you conduct an eigenvalue analysis, then you can see the frequency and corresponding eigen vector that is something like this. So it's like banana mode in a common language. In a banana mode, for sure this is important, particularly if the system is loaded in this banana mode direction, like it is, because there's a hydraulic cylinder connected to this direction. But when you look at another modes, this is example the modes where deformation is in transverse direction. In this transverse direction, probably not that important for us because most of the loading will be in this direction where the cylinder is attached. And for that reason, this may be the mode that you can ignore. So maybe you don't need to worry about this mode at all. Well, depending how is the rest of the structure, but basically not necessarily so important. This is a mode, the same direction that where the cylinder is connected. So this too probably is very important. But if you go higher and higher modes, soon you started to get the modes that are not significant anymore, any longer. Here is a mode that is having the fairly high frequency, This may be important when you look at the details related to hydraulics or connection of hydraulic cylinders. So maybe this is kind of needed, but generally speaking, this becomes to be less important. And then there is a mode that you definitely do not need. So here the deformation is associated to this joint connection, and I don't think that this makes any difference in terms of dynamic performance of the structure. Now, this is kind of the mode that you can easily ignore. This was a transverse direction, so you probably can ignore that as well. Maybe this as well. Just using the few modes, you can have acceptable accuracy. Acceptable accuracy, and that's what we are after. Okay. Recap. I have a recap, but I'm not going to step to that right away. First, I want to discuss about the real-time simulation, but practical matters. One practical matter. Remember, this is a. I guess if there's one equation you need to know from this course is this grading equation. So what are the components that makes a difference to your final grade? Is a written exam. Written exam, how you can do that, we will take a look at that in the next slide. Simulation work, which is a mandatory thing. There's been some discussion regarding the simulation work in the model. So Suraj was kind of hoping you to participate some of the meetings, which I think it makes sense to do it. And he will do his best to help you to finalize the simulation work. Weekly homework and in-class quizzes are extras. So those are not mandatory items, but if you decided to do it, good, because they can improve your final grade. But the practical matter that I would like you to know is this. Written exam, you can do in two different ways. So you can participate these 2 online midterm exams, which is what I'm highly recommending you to do. It was mentioned that the last exam is in a week 51. That's what I would like to change. I would like that to be in a week 50. And reason is that if you're going to have it in week 51, you will have a bunch of other exams, and maybe you don't have enough time and energy to focus on this exam. So I'm thinking the rescheduling makes sense. I hope you agree. If not, send me an email. And then if there is some difficulties you to participate these online exams, which I doubt, then the alternative, this is the first alternative. Second one is to go to final exam. The first option is 17th of December, and then in February and in March. Those are the 3 options. February and March. So hope this is okay. And if not, let me know via email. Let me see if there's any comments in chat window in this regard. I guess not. Guess not. All right. No comments. Yeah, well, how it goes, how the practicalities goes in a midterm exam is exactly same that in the first midterm exam. 2 attempts, highest will account. 2 attempts and your highest will account, and you will have a week time to do it. I mean, to do your 2 attempts. So it should be enough. It should be clearly enough. Yeah, so it's get started. I need to check I guess that I cannot check my calendar right now, but week 50, if I remember correctly, is a Monday, December 7th. Yeah, right. And then that's when the exam will be on. So just Monday, 7th December, 7th of December at 005. So right off, yeah, that's what it is. So check the chat window, 7 to 13th of December. So I will put it on in a Monday night, and I will close it just before the midnight on Sunday. So yeah, so you have 2 weeks time to take a look at the recordings again and finalize the project work. Highly recommended that you do your project work before that. So once you're done with your exam, then you're done with the scores, and that will be really outstanding. So think about the Christmas. That's the way that every responsibilities regarding these scores is done. That will be beautiful Christmas. You don't need snow and you don't need the Santa Claus, but if you can complete the course, that will be your Christmas present. So deadline for simulation. Uh, oh, I got that. I got no data anymore. Hmm. God damn it. To have a connection. Oh, I'm back in an excellent connection. So simulation deadline is, I think, 15th, if I remember correctly. Can you please double check that? Yeah, it's a 15, so I can see that from the chat window. So then you're gonna be you're gonna be the master of rotating of particles. So you can go and explain the planet how the particle can do the rotation. That will be your master. Right. Okay. Let me take this off and explain you something else. Okay. Now this is a few slides about how is a real-time simulation, real-time simulation and games. Actually, I don't think I have that much time to explain about the game technology to you, but we're gonna look more about the real-time engine, which is absolutely no secret because it's a multibody. It's just that the multibody will be synchronized to real time, and that's all you need. Oh no, I need to change the color because maybe this will do it. Yeah, this will do it. Real-time simulation, not so much about the games. We're gonna look a little bit about the game technology in the framework of product development, but mainly the focus is in real-time simulation and what is that we can do with this simulation technology. I mean, the knowledge that we gain in this course to be able to solve the dynamics, how that can be used in different product processes, not necessarily in product development. I mean, that it, of course, it fits really well the product development, but are there other product processes where we could possibly use this technology? That would be interesting to learn as well. Okay, so let me just take one window off that I can see your comments. So I need to make this a bit smaller. Just a second. Here. Okay. Now it seems to be everything seems to be okay, streaming wise. Okay, so three matters that I would like to explain to you. Just three matters. So a little bit about the background, a little bit about the product processes. So what are these product processes we can actually use these skills that I would like you to learn. That's extremely important. And I would like to look at this in a broad perspective. So more than product development. And then conclusion finally. So this presentation or this real-time simulation is a part of the LUT organization. So how that's possible? That's possible because in the current organization of LUT, you know that we have three schools. Maybe this is a little bit boring, but important to me. So we have three schools that are business and management, energy systems, and engineering science. And I think this was 6 years back, 7 years back, we got the new rector to university. And what happens when you get the new rector? The next thing is that you will get the new organization. Same holds in the companies as well. So you get the new director. The next what follows is a new organization. Same happens in LUT. This time, so the director wanted to organize university to matrix form. And that meant at the time that in addition to these three schools, there were research platforms trying to encourage the internal cooperation. And and there was an open call to make a proposals about these platforms. One of the platforms that I proposed, actually I proposed just the one, was called Sim Platform. Sim Platform, as the title implies, is all about simulation. And the idea is to take these simulator-driven design methods to another level by focusing on real-time simulation. So real-time simulation was really in a focus. Well, this year is the last year for the Sim platform, but we learned quite a bit of things. We developed quite a bit of things, and those are the things that I would like you to know to learn. So this actually takes you close to research that is conducted in LUT. And I kind of feel that it's important you to be aware of that because a few years back, we got a little bit of complaints. I mean, teachers, we got the complaints from the student union that we don't explain to students what is exactly is the research we're conducting in LUT. This is a very pleasant topic to explain because it's very close to real life. So that's why I'm going to spend next, I don't know, 40 minutes, 50 minutes to explaining what is a deal with the real-time simulation and what is a deal with this sim platform. Okay, so a little bit about background. This is heavily related to Industry 4.0, so fourth generation industry, this one here. And what's the idea of this is that we have, it's called cyber physical systems, something that there are computer-based physics if you want to cut the corners. So the machines, they have their own understanding about how things are moving and what happens. That typically is model-based. Could be some other solution too, but typically is a model-based. And if you look at what are the other generation of industry, those are something that you're very much familiar with. So steam power, mechanical solutions, that's the first generation. Mass production, Ford production line. Electricity, that was a second generation. Computer and automation was a third generation. And now the Industry 4.0 is cyber physical systems. So let me ask you this. Industry 4.0 is about cyber physical systems, mechatronic systems, 4G internet connection, extensive use of electric drives. Just what I explained to you. Game is on, so let me put it Joker Div online. Oh, it's up and running. Oh yeah, I can see that some of you already entered the answer. Let me see. Game is on. 100%. So guesses are getting started from the 100%. Come on. No. You can't. No, I don't think that's the case. So all saying 100%? I don't think so. I don't think so. There's a high temptation to make a bet. That is not the 100%. That is, oh yeah. So now there is something else than 100%. 95. I like that. My guess is this. 95. You guys are all saying that is 100%. So let me see how many students I have today. 56. What is going on here? So where are the rest of the students today? Let me see how many people are following the streaming. 65. 65. But it should be 80 something. So where are the rest? Okay. So I got a total of 62 students today. And I'm expecting 10 of you to enter your answer, and then we will go again. Okay. Yeah. There's this. So there's a little bit of strategy here. So if you say that, okay, the success rate is not 100%, and then you intentionally enter the incorrect answer, that's a risk. That's a risk. You shouldn't do it because that you can gain more if it is 100%. Okay, 5 students are thinking, so soon we're good to close this game, and then we will continue. By the way, how is my voice today? Is it any difference? Can you hear any difference? Or is it all the time same? Because the new headset, this is if nothing else, this is more comfortable to wear. So, okay. 2 students. No comments about my quite clear voice. Sounds better. Nice. Okay. So 2 students, I need to wait. So I cannot release the solution to you right away. So let me look at something else. So I'm sure you heard this story about the digital twin or digital threads. Those are the things that are very much in fashion at the moment. What is that they're representing? Well, they have a very different kind of interpretation depending who is that you ask from. But in LUT, the idea we have in a digital twin is that it has to be something that there is a data involved. The data may be coming from simulation. It could be simulation-based data production. It's really is important that there is a virtual representation of some kind, usually more than just figures. It really helps if there is some dynamics involved. So the data is the first thing, and understanding and predict. So if there's these 3 corners, that's what we're calling as a digital twin. I know that this becomes to be a little bit unclear to you based on this short explanation, but we're looking at based on the video that is produced by Mevea. And now you may wonder what's the deal with this Mevea? So how did this important to me? Well, it's not really very important, but it's just the university spin-off that is specialized to real-time simulation. They are offering these solutions for companies that allows companies to build models that you can run in real time. Why? Well, that's you're gonna learn later today. So I'm missing 1 student in my in-class quiz. So the last one, please hurry up because I would like to show that. So let me play the video for you and let me see how is the voice. Yeah, I hear the voice. Yeah, that's the problem. You don't hear the voice.
Manufacturing machines can be a complex and costly process. Assembling the first prototype.
Not good because I hear the voice. It comes to my headset, but you don't hear it. Can I somehow? No, I cannot. So you hear the sound. Oh, okay. So you hear it. Great.
Manufacturing machines can be a complex and costly process. Assembling the first prototype from parts that haven't been developed or tested together will often cause problems, and getting everything to function properly may require significant amounts of materials and effort. Nobody wants to be known as the manufacturer of poor and unreliable machinery. So wouldn't it be great if you could build your first prototype secure in the knowledge that it already has hours of thorough testing behind it? Well then, may we introduce you to Mevea. Mevea combines all plans for your machine into a single virtual model called Digital Twin. This includes all the components necessary to build your machine, such as the interface to the real control system. The digital twin that is created is a virtual physics-based representation of your machine, capable of simulating its behavior and use in real time. The Mavea software simulates real-life physics, so the machine can be tested in different environments and on the actual tasks that it's designed for. You will be able to detect potential problems before anything is even built. The digital twin can be inspected and modified when necessary, and stakeholders can also get involved in the development process at an earlier stage. The rapid development iterations that the digital twin enables will result in fewer prototypes, reduced costs, and faster lead times. Moreover, Mavea's solutions allow operators to use the simulation for training, which means they will be qualified to use the machine before it even exists. The digital twin lives and evolves throughout the life cycle of the product. Once connected, the digital twin can analyze the machine's use and behavior in the field and provide vital feedback. This data can also be used to develop the product further. With Mavea's digital twin software, you can develop even the most intelligent and complex machines with ease and change the way you engineer and operate your products. Read more about Mavea Digital Twin on our website.
Okay, so I take it that you heard that you were able to follow the whole story. That's great. I thought that the voice always coming to my headset, but obviously there is some secret technology that is passed by me. Anyway, so it says behavior and use in real time. Is that something that is useful for us? Well, it is actually. And we're going to look a little bit about how this behavior and use in real time can be applied in the different product processes or steps in the product processes. Those are the ones that are mentioned here. So the planning, concept design, more like product development tasks, validation, production, marketing, sales, operation, in service. Those are the things we're going to look what is that we can do with this real-time simulation. And then one more important thing, how the data that is gathered from the measurements could be used in, well, product development, but how it can be used to provide the service business to customers. Maybe there is some data-based solution that would be nice to kind of extend the business. So those are the things we're going to learn. So yeah, basically like mentioned earlier, so it's a product life cycle management, but even a little bit more than that, because we can provide something that is otherwise is impossible to offer. And that will be something that we can use measurements from the field, and those measurements can be enhanced using simulation models. So, and that gives us an opportunity to have a full understanding how is a machine behavior and how is it used. That in turn can be used to optimize the energy consumption, operation behavior, and so on and so forth. So that's what we're gonna look. But let's see how are these real-time simulation models. I think this is something we looked in the very first lecture. So here is a example about an excavator and how is a real-time simulation model of an excavator. But this let me stop here. So this includes all the components you can find in a real machine. So it comes with the mechanical components, joints that are connected to mechanical components. Well, no surprises because it's multi-body based. Hydraulics. Well, we know how to model the hydraulics. Then there is tracks that are also based on multi-body system dynamics. Deformable crown, which is multi-body based. So everything is multi-body based. You just build all these necessary equations and you solve those in real time. And environment model, which, this time is just this deformable crown. This typically is a particle-based description, but let's see how it behaves. So, my drawings are a little bit of disturbing, but let's see. Now, because the solution is real time, so you can have an operator that is actually controlling the machine. And this is something that it's very useful in many different perspectives. And what are these perspectives? We will get back to that soon. Okay, so there's a question in a chat window which asks, can companies build a Mavea model based on the CAD description? Yes, they can. So they take a CAD description of mechanical components, they combine them together. They can introduce the hydraulics, and then that's about it. Then the model is ready. Then measurements from the field, how that works. So I have slides in that regard a bit later, but it's something that is very, very exciting. So we have sensors that are reading, say, acceleration from the certain components. Those can be used as an input to our models, and the model is then reproducing the motion that happens in reality. Why we do it? Because model gives us a full understanding what's going on in the machine. So it gives us an understanding about every single component, full state, if you want to speak about it in the terms of control engineering. And once we know the full state, well, then there's a lot of things that we can do with that. We can give extra information to user. We can avoid the misuse of the machine. We can use that in software development and testing and so on and so forth. So that's what we're going to look a bit later. So these environmental models could be based on real environment, like this one here. I hope you hear the music. I don't speak if the music is on. Okay, so that was a photogrammetry-based environment model. So, and it was made by 3D Talo. And we, of course, because it's at Stefan's environment, we made another model where we're putting our real-time simulation machines. Maybe you can recognize this one. Oh, let me see. Yeah, it's coming. No music this time. So do you recognize the place? Yeah, it is a university environment. This time the excavator is operating in front of the university. So this too was made in using the photogrammetry. So drones that are scanning the environment. And once the drone are done, then this is how the environment look like. Yeah, this is Skinnarla. So this is definitely virus-friendly way to visit in university. And it looks fairly realistic. It's missing cars, it's missing people, but it's okay representation. Yeah, so maybe you can wave from your apartment window so we can take a look where is that you are living. So that's a university environment. Again, photogrammetry based. This kind of stuff, even though that is just an environment, sometimes it's extremely important, particularly when we are looking at some of the industrial solutions, and sometimes when we really wanted to make one-to-one model, including the environment. So they are sometimes definitely needed. Okay, so the real-time simulation model. So let me move on. I know that I'm a little slow today. And by the way, now I have this. Okay, so one student is missing, but it's been missing already quite a while. Is it still possible to change my answer? Because I would like to change my prediction to be 85. 85. Oh, where that disappeared? Where is it now? Here, 85. And then I will get back to this this comment in chat window. Okay, so you guys ready? I was wrong. I was very much wrong. I thought that this, I'm surprised. Very much surprised because there is a high temptation to vote mechatronic system because the core is entitled as a mechatronic simulation of mechatronic machine. Okay, but the success rate is very high. Not 100%, but it's very, very high. Good job. Let me see if we got any winners. So the correct number is, well, I know it was 97, but now it's 96. 96, 97 doesn't make any difference. Oh, yeah, so there's actually one winner. So let me see if anything else. Yep, yeah, just let me see, one winner at least. It will be so nice to announce the name of the winners, but it is what it is. 7. That's it. That's it. Just the one winner. Okay. So, so then, yeah, 86 is okay. So I might make that as a. So that's going to be considered as a winner as well. Okay. Two winners this time. Yeah. Okay. But there was a question about accuracy. Where is it now? So it's up here. Yeah, well, the thing is that this photogrammetry, it's based on the drone, so the drones are scanning the environment. So it takes a bunch of pictures, and the three-dimensional representation is made out of these pictures. Okay, 98 will be accounted as a winner as well. So who we have at 98? Yeah, we better have some tolerance. You're right about that. So I guess it was you that voted that. Let me just double check that. Where is it now? No, I don't see this answer. Here it is. Yeah. Yeah, three winners. So we have three winners. Great. So let's move on. So what is that we have? What is that we supposed to have in these cyber physical systems or real-time simulation that are accurate representation of reality? Well, of course, we have to have a mechanical component there. We're supposed to have an actuators there as well because those make a significant difference in terms of dynamics. Control system sometimes needed. User makes a big difference. You know that there is a significant differences between the different users and working process as well. So everything you will see from this on, these 5 matters are included. So then finally, let's move on to these numerical examples. These product processes that I'm going to take a look at. So I'm going to look at the product processes, product development first, then one case from the marketing, which is actually focused on user training. Then we're going to look a little bit about the service business. That's where we can actually use these measurements. And we can enhance measured signal using the simulation models. And then new business opportunities, we're going to take a look how is that artificial intelligence could be combined with simulation models. One thing that I have no example, but is important too, is that it helps the people to communicate. It's giving a common language. So the simulation could be considered as a common language that, the specialists making hydraulic circuits and hydraulic designs can understand what is going on in a mechanical design. So those are the things that helps. So we thought that this kind of course and this kind of game-like environment would help people to appreciate the mathematics. That I'm not sure about that, but it was more like dreaming rather than anything else. Okay, let's get started from the product development, and let's see how is that we can use that real-time simulation in the product development. The first thing and the first important observation is this. You know, as a trend, this is my this is not the fact, but this is my interpretation as a trend. You know, life cycle management, product development is moving away from emphasizing the technical aspects. Technical aspects are still important. I'm not saying that they are no longer important. They are still important. But one thing that comes into play is user experience, and it becomes to be very critical matter. And just to give you an example about phone business, you know, you saw that I have the iPhone, and for sure I haven't purchased the iPhone because of the certain battery technique they are using or the certain CPU unit that they are using. Not at all. I don't care about this thing, but I do care about the expected user experience. And expected user experience is becoming to be important in the heavy machinery as well. So still it is true that people are asking about technical questions and technical specs, but the expected user experience is the one that is emphasized significantly. And if this is emphasized, then that's going to be very, very difficult because user experience is mostly about matter of feelings. You know, if you look at, like, just to give you an example, if you look at car magazines, the way they are evaluating the different vehicles is, okay, this car feels like quality one, feels like solid, it doesn't feel good. But what is this? Like, how we as an engineer can understand feelings? That's mission impossible. You know, think about somebody in the field of mechanical engineering and feelings. No, that's not getting along very well. So this is not going to be a very easy thing to do. But this is where the real-time simulation comes into play. This is where the simulation comes into play because it could be used to interpret the feelings. How it goes? It goes simply such that you will ask customers to try different products because it's going to be real-time simulation models that is heavily physics-based. And then you ask, do you like it or do you hate it? And if they like it, then we can proceed in that road. And if they don't like it, then we can introduce some changes. So there's no need to build a physical prototype, but you could get an idea about these feelings using real-time simulation. Concept is this. You know, in a conventional product development, you know, we have product development team here. And the purpose of the product development, this is my interpretation, and this is what I'm going to ask in my next in-class quiz. So the purpose of the product development is to serve the customer as well as they can, kind of fulfill the customer needs. That is that they wanted to do. So the crucial step here is to understand what is that the customer wants. That's not that easy because sometimes the customers, they don't have a technical background and they are unable to express their desires in a technical terms. They could say that I want to have something that is solid and feels good, but I have no idea what that means in terms of technical design. Okay, so product development, try to figure it out what is that the customer needs and how is that they do the work today. Well, that today they're having different kind of questionnaires, interviews, and so on and so forth. They're trying to get the picture. And once they get the picture, then they're using these digital tools, including multibody system dynamics, to kind of speed up the product development. Speed up the product development. But in the worst possible scenario, you know, these digital tools are just helping us to make wrong decisions faster. Because what is critical is this box here and how well we understand this box. What is it we can do to solve this problem? Well, we can take these digital tools and build a bridge using the digital tools between the product development and customers. And now we can introduce the new ideas to customers without building the machine. So it's like a game. So we say, okay, here's a new product. You like it? You can try it and try it in a different scenarios and figure out if you like it or not. And then a customer come and say, yeah, I kind of like this feature, but I hate this feature. Or you can even open some of the design parameters to user to allow the user to modify the model. And if the user can modify the model, then the product development team can monitor what is it the way that they are monitoring they're modifying the model. And this is going to be the next dream product. Of course, it's going to be a statistical thing, but using this statistical thing, that's when you could get the better understanding about the customer needs. And then the product development can come into play and fulfill those needs. And that's the whole reason. That's the whole game. Okay, so here is a little bit an example about that. So we have built a simple games, excavator games, where user can modify the certain features of the excavator, changing the hydraulics a little bit, and then figuring out, how is that different pockets behaves. And then there is a competition to load this industrial hopper as fast as you can. So we're monitoring the productivity. And that's a simple game which helps to get the better understanding what is that the customer wants and what is the most optimal solution in terms of productivity. So selling services and products, that's what it is. Good comment. Okay, these are the features you can modify, but my next in-class quiz is this. Purpose of product development based on hockey, because this is not necessarily a science. Fulfill the customer needs, use sophisticated simulation tools, conduct complicated research, build more complicated machines. What is correct? And just a second, I need to go to my soccer team. So it's on. Game is on. And I see that the answers are about to come. Okay, actually, today we have 71 students. That's a good number. That is a amazingly good number, because I was expecting that this is the last lecture. So we got like 7 views. But 70 is 71. 71 is a good number. So I'm very proud of not myself, but you, because this is for you, definitely for you. And again, the game is on and the guesses are 100%, which I don't think so, because look at the options. It's not that simple, not so simple. And while you guys are guessing, let me proceed in my explanation. And let me move on to another subject matter, which is marketing. Like mentioned, I think there's one of the comments in the chat window that this could be used in a marketing purposes. Yes, it can. It can be used in a product showcases. Showcasing what are the technical features of the particular product. Definitely it can be used for that. It can be used for customer value analysis, but I don't know how you can make that happen, because that's definitely is the business people talking. I'm not that much involved in that. So we're going to look shortly about user training based on real-time simulation model. And I'm going to play you one simple video. This is a video that is, let me think. This is 17 years old. 17 years old video. So 17 years ago, it was possible to make a simulation models, real-time simulation model like this. So look at the environment, looks okay. And the purpose of this model was to train operators of that crane. I clicked something accidentally. To move containers from harbor to ship and ship to harbor. So it was all physics-based, not hydraulics involved, but the idea here is to show you that this was possible 17 years ago. So think about how they look at the moment. Well, more sophisticated. But the visualization is okay. It's not outstanding, but it looks semi-realistic, let's put it this way. And some of the features are kind of clumsy. Like you can see the wire ropes models are not so great. But obviously they will do the job, because this is being used to actually train these operators to use this crane. So it's doing the job. Okay. Uh, yeah, user training, that's definitely used in the flight simulators. That's definitely the common business, is a common practice. This is in development phase, and development phase you see that this is kind of like weird looking because the joysticks are game joysticks, not really high quality ones, but it was made to develop this system, and they made a top again. Yeah, the flight simulators, they're also physics based, because if the training simulators are not physics based, if they are just like animation, it makes no sense. Yeah, that's another good comment, is the Formula One. They do it in a Formula One too, and those are physics based as well. So you can build the one as well. So, and yeah, you're right about that. Joysticks that this you can see in the figure, they're not definitely the latest model. This is an environment that is where the operators actually practice to use this simulator. Look at its really heavy duty, really heavy duty. The huge hydraulic cylinders. Motion platforms are no longer made like that. Screen is made such the way that is you're looking downwards like you do in a real case. This is another machine. I think this model too is like 15 years old. And the idea was to move these boxes, piles. Oh, my mistake. I shouldn't do the drawing. So let me go back where I was. Here. To move these boxes from harbor to ship and then back and forth. Let's look at the contact models, how they are. And then we're done. But user training. Oh, okay, so this guy did not pass the test. Same here. I don't think it's a purpose to load the ship like this. I doubt. Then let's see. Oh my God, so not good. So this was a full of flat TVs. Now they're all broken. You can change the weather condition and so on and so forth. So that's one option. One thing you may consider to do. Yeah, or maybe there was a Mercedes in a container. It's a lightning condition. So let me just go and get a little bit of more water, and I will be back with you. Yeah, I see that my water consumption is very high, but the reason being that what I'm doing like day in day out is talking, 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 and Mondays is a lot of talking. When it is getting late like today, it's kind of like hard to keep my voice up. So that's why I need that much water. Sorry about that. So I keep on drinking. Okay, but let's move on to this thing that people already ask. How did this possible? And this is a matter related to fault diagnosis, embedded models in maintenance, or for maintenance, and digital twin service. So how is an idea here? An idea is simple. So you can get the data from the measurements, and you can use the data for a number of different purposes. The one simple, obvious thing that you can do with the simulation model is that you can build the library of symptoms. You can introduce different kind of faults to your models, and then you can see how the machine behaves if this particular fault takes in a place. And based on this kind of symptoms, you can have an extensive library that you can teach to artificial intelligence to be able to detect what's going on in your system. And then once you get the signal from the field, from measurements, then you can compare whether or not these symptoms corresponds to certain failure mode. And here's just an example. So it goes in such a way that, let me make the voice a bit lower. So here's the hydraulics. And look at, by the way, how the hydraulics is modeled. This is modeled by using these drawing symbols. And that's very, very modern way to model the hydraulics. So you simply put the different kind of symbols in a panel or a screen. You connect those by hoses, and then your hydraulic circuit is ready. And you can even visualize. You can see when you're moving this direction valves back and forth. You can see how they are connecting different boards. And that helps you to measure the pressures in different locations. And now we could simply break some of the hoses, introduce some faults, and see how the system behaves. These are, of course, very unrealistic cases, but just that you can get an idea. So here's when when the hoses will be broke, or the behavior becomes to be a little bit weird. Okay, so now it goes like that. So more hoses will be broken. Now this is back in operation, back in live. And now it's completely dead. Okay, it's just a simple idea of what is that you can do with the simulation models. But the thing that is interesting is this, because if you can use a measured signal as an input to a model, then you can use your model to dive in the machine and see different interactions and see how the machine actually performs. And that's possible too. And that's what we're doing at the moment in research-wise. So again, idea is this. So we have an actual machine. So we have real sensor, and this sensor could be pressure sensor, it could be accelerometer, it could be position sensor. And then we have a simulation model that is as close representation of reality as possible. It's never going to be one-to-one same. So that's not just possible to do one-to-one same, but that's okay because it doesn't necessarily need to be one-to-one same. What we're going to do is that we have the same measurements in a simulation model than in a real system. We are looking the difference from these measurements, and the difference will go to system that is based on Kalman filters, state space observers. And those are the ones that are correcting solution. Once they're correcting solution, then we're gonna add that to our actual model solution, and then we get an estimate. And this estimate is the one that we can kind of dive in the machine and see how the different reactions are in the machines, how the forces applying in the machines are. So we can even use this technology to measure the digging forces that you can have in an excavator or something else without using force sensor. And that's something that is very, very exciting because we can first of all lower the amount of sensors. We can get this indirect information that could be force-based or pretty much anything you want. And that's we feel that is something that we can actually offer some additional information to users that otherwise is impossible to get. So here, let me explain the system again. So I have here two models, the one that is representing the reality, another one that is representing the state space observers. And now we have making this system such the way that they are not synchronized with the Kalman filters. And there's a little bit of phase difference in the beginning of these models. Like you can see, the green one and blue one are not getting started from the same phase. This is representing the modeling differences that you can easily find in real life. And how they behave? Well, they behave, okay, so they behave like this. So, the measurement and the real system becomes to be one-to-one almost immediately. And when they becomes to be one-to-one almost immediately, then you can use this technique to say, plot the forces from this joint, or pretty much anything you want. That's the idea. Here is the hydraulically driven 4-bar mechanism, but we are estimating the forces produced by hydraulics using this virtual sensor technology or state space observers. I don't know what's the correct name for this technology, but just something you to think about. These two model based. So multibody dynamics becomes to be quite handy. What about this? A new optimization, system level optimization, enhanced automation. So in enhanced automation, one of the things that are very exciting at the moment is the use of artificial intelligence. Problem in artificial intelligence is the fact that artificial intelligence needs a huge amount of data. And this data production using the measurements, it's possible, but it's not very straightforward. So we've been using these physics-based models to train the neural networks and solutions based on artificial intelligence. And with that, we can make systems to be more or less automated. That's something that is quite exciting. There's another, even maybe more important point of view. And another important point of view is that right now, when we have these complicated real-time simulation models, most of the time that happens inside of the computers is that they are waiting. Now I see that I have a streaming problem. I guess that I'm back. I'm back. Okay, so most of the time they are waiting. So all these equations are solved, and then they are waiting. And what is that they waiting? They waiting the real time to hit the same spot. Then they can read the signal from the joysticks or other sensors, and then we will proceed in a time again. Then they will wait, and then they will do the computing. Then they will wait. So it's quite a bit of waiting. And think about if they don't wait. So what will happen? Okay, I got the information that no data. Streaming will end shortly. Warning. The data stream is much lower than minimum requirements. Let me see. Not looking too promising. We still have 66 viewers. No data. Not receiving any data anymore. Why? Okay, so let me go and check how is my iPhone doing. This should be okay. Let me see. No, it's still the same problem. It's not. Yeah, I like that idea that I should open the window in my basement. Okay, so let me see. Maybe finally gets better. Still an error here. Too bad. Still not enough data. But I can see that it's already going out, so it's not as bad as it was. Hope it disappears soon. Okay, better now. So it's still the warning signal is in my screen, but I guess it is getting better because at least what I can see that my head and my hands are moving when I'm following the streaming. Okay. So I was here in artificial intelligence, and I was about to explain, most of the real-time simulation cases, there's quite a bit of waiting. So waiting that the time hit for us. What happens if we don't wait? So that actually gives us a kind of like an opportunity to see how is the future? So see, what happens in the future, because we're going faster than the time, computing faster than the real time. That's what it is called. And now if we really gonna compute much faster than the real time, then we can see far in future. And also if we can compute a huge amount of faster than the real time, we can have a number of different motion scenarios. Each one of them can be projected to future. And then we can have an algorithm based on artificial intelligence that is selecting the most desired motion. That's interesting. And that's exactly what we wanted to do and trying to do with the machines at the moment. So see the future, giving the projection in the future and selecting the most desired motion in the future. That I think it is a very exciting technology. And if you guys have seen the movie Terminator, I think that's what the Terminator is based on. Okay, so let's take a look at an example. So our colleague in Aalto University is helping us in this regard. So this is a predictive simulation. So just to get an idea, what is a predictive simulation? Here's a kind of like an Angry Birds game. And the idea is to move all the boxes. You can kill the game if you know what happens in the future. So now there's 1,000 times faster than a real-time computing. And the faster, 1,000 times faster than the real-time computing, you can see the consequences. So you see what happens in the future. And when you see what happens in the future, the game becomes to be ridiculously simple. Another example is use, okay, let's skip this example. And let's see, this car is trying to go over this heavy traffic without hitting the other cars, and conventional methods are not capable to do it for you. What if you can predict what happens in the future? These predictions are these yellow curves. So now you can make it happen. So that's possible with this predictive simulation. Predictive simulation and something that is teach in advance to real-time simulation. That's something that we feel that is extremely interesting. Extremely interesting. Here's a little bit about what this machine learning can do for you. So when they are teach in a different ways, an idea is to make this kind of a human representation to walk as stable as possible. So let's see. Let me take. Here it is. So this is where things getting started. So this is the first attempt, and it looked that this guy is doing okay, but is heavily drunk. And now, so once this learning methods is added, so it's getting to be stabilized. And look at this. So after a little while, it's getting much better. Same concept coming from the game technology, but we would like to use those in multibody system dynamics. So here we have an environment that is called MGym, Meve OpenAI Gym. And it is basically to use different kind of artificial intelligence algorithms to control different kind of multibody-based models. So I know that I'm running out of the time, so I'm going to skip some of the examples and just to show how the excavator behaves. So in this excavator, there is no human interaction. So no human is touching this. So everything is based on physics-based simulator and then artificial intelligence. And it's capable to do the job, because the job is to move the dirt from the ground to this industrial hopper. So it's obviously capable to do it. Okay, so finally, ready to take a look how is our in-class quiz here. So in-class quiz, I'm missing 2 students. Okay, so I need to go back to the game. So I see how are your guesses today. My personal guess is 65. No, 85. 85 is my personal guess. 85. So here is a game. I see your lottery coupons. Astonished. Astonished. This is Really, really nice. Really, really nice. So it seems that you guys are listening to me. I'm impressed. So, but did we get the 96 correctly? We got 95, 95 at least. 95 would be considered as a correct solution. Let me check this off. Goes here. Here 95. There was a 95. I saw it earlier. 96 is, we got exactly correct. So 96. And the same winner again. Did I miss now something? No, no, that's right. That's right. Oh yeah, we have several winners today. Okay. Yeah, yeah, I saw that. So now you guys are doing really good in the lottery. So let me conclude this topic because I still need to explain what is that you can find in next midterm exam. So the conclusion is this. Real-time simulation is all same thing. So is all these boxes still needed? We're simply going to synchronize this all these boxes and all these solutions to real time, and that's going to do it for us. If you want to learn more, here's your way to do it. Look at this. So you can log yourself to address that is lut.fi/sim. So that's where you can learn more material about the sim platform. These are the two courses that I'm delivering. So 2 courses only. The one you learned already, and another one that will be in the next semester, starting from January. So yeah, I know that you guys are excited that you are scoring so well. I would love to offer you a beer, but you know that the university is in a remote mode at the moment. Didn't you get the message from the rector? He said that no teaching, I mean, the only urgent teaching in university anymore. But anyways, the winner, next time if we see in a face-to-face, I can offer that to you. Okay, so here are the companies and other teams that we're cooperating with. Let's look at some of the nice animations here. This is L, U, guess what? T. Okay, the final one. This is the last, but I want to show this to you. Oh, look at this. This guy is seriously lost. He's our rector. Okay, and then with that, I'm gonna move on to summary PowerPoint presentation. So let me take this off completely and put this back. Okay, I know that I'm kind of running out of the time, but I don't have that many slides to go anymore. So these are the matters that I'm expecting you to master when you get into next midterm exam. So there's only 4 entities, 4 things, and they're not the same level. So this embedded technique is still something about the multi-body system dynamics. It's a kind of the details. It's rated as a 3-star. You should definitely put all your efforts to hydraulics. Definitely needed. If you are short of time, focus on that. And the deformable bodies, skip it if you're in a hurry. But if you want to score high, you need to take a look at that as well. Real-time simulation, yeah, you can study that, but you could look at the video one more time and that's all you need. There's no written text associated to that. Okay, so short summary. Embedded technique. What is a deal with the embedded technique? Shortly, idea is to express this virtual displacement such the way that is kinematically admissible. And now I can see that my camera is, oh, it's back in live. So it's back in live. So this needs to be kinematically admissible. How you can express this to be kinematically admissible? You can make it happen with help of coordinate partitioning. So you divide your coordinates to dependent and independent parts. And you do the same for Jacobian matrix, and that helps you to find a relation between all the generalized coordinates and independent generalized coordinates. That's what makes it kinematically admissible, right? So then you will do the final thing, which is expressing the acceleration also by using independent accelerations only. That's going to be your equation of motion. Okay, so I see that my camera is now completely done, so it's no longer. Oh yeah, it's still moving. Seems still to move, but it's lacking like no limit. Okay, that's embedded technique. Hydraulics, properties of fluids, line fluid theory, flow types, modeling of hydraulic components. Those are the 4 things that I'm expecting you to know. Properties of fluids. Please focus on the bulk modulus. Viscosity is something that it's good to know, but don't focus on that subject matter. Make sure you understand the bulk modulus, and make sure that you understand that it's representing the flexibility. Flexibility. Okay, so there is still a connection problem. No. Okay, I don't know. I got no complaints in my streaming window. It says excellent connection. It seems that the camera is the one that is now not cooperating this time. Okay, the bulk modulus, please focus on that. Okay, then the bulk modulus, how it goes in details. It goes such the way that you are looking at, the system that consists of number of containers. And using this number of containers, you're capable to, yeah, I see that you have still difficulties to see me. Okay, and I see that my way I'm moving is not smooth at all. Okay, so different containers, and using these different containers, you can compute something that is called effective bulk modulus. That is describing the effectively flexibility of fluid and containers. That's something you definitely need to know. All right, then a couple more slides to go. Line fluid theory. Very, very critical. Line fluid theory, look at this. So this is definitely something that you must know. You have to understand what is that this equation describes and what is its limitation. So this equation describes the pressure as a function of time. So it's not pressure, but it's a way to compute the pressure. And the component here is effective bulk modulus, the size of the volume, flow rate in, flow rate out, and possibly change all the volume itself. I could easily ask, like, please explain what is a limitation of this equation? What is that is not describing? And or I could say that, okay, please explain the components in this equation. And I see that there is a comment in a chat window which is asking, like, is this material coming to Moodle? It's going to be coming to Moodle. Okay, so it's not coming early. I'm gonna upload that to this evening or tomorrow morning at latest. Then the different kind of flow types, we can deal with the laminar flow, where the flow rate and pressure difference are linearly related, or turbulent flow when these 2 items are quadratically related. So how that goes in practical in different cases, that depends heavily on what kind of system you are looking at. Modeling of valves. So we're using semi-empirical approach where we're getting started from analytical equation, and we're converting analytical equation to be in a form that parameters can be obtained from manufacturer's catalog. That's what it is, simply talking. And we look at direction valve, we look at a little bit about the pump and the cylinder. So please take a look at these things. Deformable bodies, we concluded already earlier today, in the beginning of today's lecture. And the real-time simulation, try to keep this picture in your mind, kind of like idea that the real-time simulation can be applied to wide variety of product processes. My last slide is this. Hope to see you soon in another course, which is called Simulation Laboratory course. This is the course that I like a lot. Why? Because here we're going to speak about, okay, what are the practical applications and what it means, when we can do this really nice simulation models. we're going to learn one theoretical matter too, and that's related to the description of flexible bodies. We learn how flexibility can be accounted, and then we're going to learn a little bit about the contacts, a little bit more about the real-time simulation, a little bit more about this and that. So it's like mixture of things, but I like it a lot. That's in my mind, it's a great course, but that's in my mind. Okay, so I see that I kind of have 2 minutes left in today's lecture, but you know what? I can be flexible, easygoing guy, and I can even close earlier than 5:45. So let me see if there is any other comments. So there's a comment about this material. So I'm going to upload the material to Moodle. Sorry that I was experiencing some internet connection problem today, but if it turns out to be extremely low quality recording streaming, then I have the recording that is in my computer, so I can upload that to YouTube. That should be quality-wise better than the streaming. Okay, so I have nothing else to say, so I want to thank you for participating. It was a lot of fun. Hope to see you in a simulation laboratory course. And like was asked, this was asked in the very beginning, when this course will be, that will be beginning of January. So it's going to be period number 3 and period number 4. So it's closing just before Labor Day, Vappu. Okay, so I'm going to send you invitation to Teams meeting. So see you soon in the Teams. And we do not see on next Monday because that was our last lecture. All right, you guys take it easy and see you soon in the Teams.